So I'll do chapters or section 6, 7 this morning. 6, 7 in terms of a section is probably the most like something you'd see in a Math 151 class. Like each problem by itself isn't super difficult. It's not like the algebra in section 6, 7 is challenging, but it's a long section and there's a variety of problems. There might be, well, you might feel like there's 5 or 6 different kinds of problems. Maybe there's really 3 big kinds of problems, and that's going to happen in Math 151 a ton if you take that course. That the sections will be long. There'll be a variety of styles of problems in the sections. So you might need to take this section a little bit slower and maybe watch half the video and then take a break, come back and watch the second half. And I'll try to tell you when I'm kind of at the halfway point where it might make sense to take a break if you're kind of being overwhelmed. Each of the first 12 problems and the second group of problems that goes from 13 through 24. So each of the first 24 problems, what they have in common is if you look at the exponent, somewhere in the exponent there's an x. Maybe it's more than just an x, but at least there's an x in an exponent. Anytime you have a problem that has an x in an exponent, it can definitely be solved using logarithms. Special problems that have x's and exponents can be solved without logarithms by just kind of writing each side with the same base. And the first 12 problems are special in that way that if you really have a good number sense, you might be able to solve these problems without logarithms. I'm going to go ahead and solve all problems between 1 and 24 using logarithms because that strategy, that will work 100% of the time. If there's an x written in an exponent of a problem that has an equal sign, you can solve with logarithms. And then the first 12 problems, I'll show you the other strategy, and the other strategy you might find easier, and it usually is easier to solve without logarithms than it is with logarithms, but it doesn't work all the time, and sometimes it's harder. So anytime you have an x in an exponent, regardless if it's more than just an x, like the x plus 2 or 5 minus x, you can solve with logarithms. So I'm going to solve this 2 ways. So the first way I'm going to solve is the logarithm approach, and that will work for every problem between 1 and 22 because it has an x and an exponent. And the other approach I'm going to do is making the bases the same. And for problem 2, you might be able to just write the answer down without doing any algebra because you know that 3 to the 3rd power is 23. But for what it's worth, I'll do both approaches here. So the logarithmic approach to solve a problem that has an x in the exponent, for this problem I'm going to write the word log. The 3 is the base of the exponent. It's going to be the base. The 3 will become the base of the log. And then I'm going to switch the x and the 27. So when I have a problem that has an x and an exponent and an equal sign, this strategy will generally be very useful. So I just wrote the log base 3 of 27 equals to x. I wrote the word log. The 3 was the base. It stayed low. I switched to x and the 27. We've done a few of these already. So now on my calculator, log base 3 of 27, I get 3 equal to x. The nice thing is anytime I solve a problem that has an equal sign, I should be able to check. So I'm going to go ahead and check before I commit to saying the answer is x equal to 3. The original problem before I did anything was 3 to the x equal to 27. I need to make sure that when I change the x to 3, that 3 to the third power is 27. Because it is, I have a correct answer and I'm done, and this method will work for every problem between 1 and 24. The second method I'm going to use is writing each side with the same base. So the left side has a base of 3, which is a prime number. I can't rewrite the left side with a different base, but I can certainly rewrite 27 with a different base. And so I'm doing a prime factor tree for 27, and my calculator so nicely tells me that 27 is 3 cubed. Remember, back in chapter 4 we did a lot of prime factor trees. I typed 27, I hit equals, and then I hit shift and the key with the quotes on it to do the prime factoring. And that only works when you're in mode 1. So if it didn't work on your calculator, if you hit the mode button and type 1 for computation, then that will work, going 27 equals shift quotes. So the making the bases the same strategy says if you can write both sides with the same base, then you can drop the bases and set the exponents equal to each other. So this strategy only works if you have enough skill to make each side written with the same base. And in this problem, it wasn't that hard. But as we get further along, it's going to be very hard. You have to be ultra clever to be able to do it. So both strategies give me the same answer, x equals 3. This answer, well, first of all, and the third strategy is just looking at the problem and knowing the answer because I can do it in my head. But algebraically, the logarithmic approach is going to work for all 24 problems between 1 and 24 that have an x and an exponent. The making the bases the same will only work for the problems between 1 and 12. It won't between 13 and 24. It'll be impossible to use 13 through 24 using this strategy. And some of the problems between 1 and 12, you have to be really clever to use this strategy. Not problem 2, though. Problem 4, I'm going to use both strategies again. And I'll always, when I solve a problem with an equal sign, I always check my answers if it's at all possible. So first I'm going to use the logarithm method or approach, and then I'm going to use the making the bases the same approach. For the logarithmic approach, I start and I write the word log. The 3 is the base of the exponent. It needs to be the base of the log. And I need to switch the 81 and the x plus 2. I could use my calculator to figure out what the log is right now. It'll turn out that it's probably a good idea to solve for x before you break out your calculator. It won't matter so much on this top group of problems because the answers will be non-decimals, but in the second group of problems, starting at 13, the answers will be nasty decimals. And if you don't, when you're using the logarithmic approach, solve for x before you use your calculator, then it'll just be messier. So I'm just going to break out my calculator and do -2 plus the log base 3 of 81. Calculator tells me the answer is 2. So my calculator says 2 equal to x. I believe that's the answer. And again, I just solved a problem that has an equal sign. I absolutely should check. So I should check that 3 to the x plus 2 power equals 81. That means I'm checking that 3 to the 2 plus 2 power is 81. I could do that in my head. I know 3 to the 2 plus 2 is 3 to the 4th power. 3 to the 4th power is 81. But with my calculator, it also checks. So I know that 2 is the correct answer. And I'm done. I won't have to use the other strategy for solving the problem, but I'm gonna. So the making the bases the same strategy, again, this is not so hard because 81 is a power of 3. I'm not going to rewrite the 3 because it's a prime number. I am going to rewrite the 81. I'm going to go 81 equals shift factor. So 81 is 3 to the 4th. And this method of making the bases the same is kind of easy when the bases are prime numbers. I don't have to be near as clever when the bases are prime numbers and if they're composite and not prime. So just like in problem 2, I have each side written with a base of 3. Since the bases are the same, I could drop the bases, which are the 3's, and set the exponents equal to each other. So I'm going to go x plus 2 equal to 4. I need to solve for x. I'm just going to minus 2 minus 2. I get exactly the same answer using both methods. And that's always should be the case when you're doing solving an algebra problem that has an equal sign. That different methods shouldn't produce different answers. Part of the difficulty in calculus is that different methods produce answers that are equal to each other that don't really look like each other. And when you get high enough in calculus, you'll do 3 pages to solve a problem. You'll get an answer, and it could very well be right, and you'll check to the back of the book to match up your answer with the author's, and it won't look like your author's answer. And it could be a real pain to make your answer and the author's answer look the same, even though they're both right. 6 would be ultra impressive to do with the second method because of the whole fraction problem. And you have to be very comfortable with the rules of exponents and how to manipulate the problems to make the bases the same. But the logarithm approach, it doesn't vary. I don't have to be horribly smart to use the logarithm approach. So the logarithm approach, I write the word log, the base of the exponent becomes the base of the logarithm, and I switch. The logarithm approach takes seconds to do because I'm relying on my calculator, so I'm doing the log base 1/3 of 27 and I get -3. So I'm done other than the checking part. So I have -3 equals to x, and now I'll go into checking mode. I'm using my calculator for that as well. I can check this by hand, but if I checked everything by hand, it's going to slow me way down because it's a lot quicker to check on my calculator. So I'm going to just make sure that happens, that 1/3 to the -3 power, which is what I get when I put in -3 for x in the original problem, that I left with a true statement. And because this simplifies to 27 equals to 27, I know my answer is correct. So in general, I probably wouldn't do this by equating the bases because of the fraction in the base. But I'll show you how this would need to be done. And then again, if you're going on the calculus, there's a whole different expectation on what your algebraic abilities are and what you need to be able to remember. If Math 142 or 151, or if this is your last math class, then this approach that I'm going to do, it isn't something that is, going to make a difference in your passing your next class. In calculus, however, just pulling these tricks out of the air, that's something you're going to be able to do, and hopefully your teacher, pulls back the tricks and helps you learn the tricks, because really algebra tricks are the key to doing really well in calculus. So I did a prime factor tree for the 27, just like I've done for the first two problems. I took the number to the right of the equal sign and did a prime factor tree. Unfortunately, I can't use the strategy of dropping the bases. Oh, this is not an x, this is 3 cubed. I can't drop the bases because they're not the same. So somehow I need to get the bases the same, and this requires being ultra clever. I should, and I'll show you the cleverness. And again, for you, those of you going on the calculus, you need to be this clever at some point in your career to do really to get a high grade in calculus. So 1/3 to the 3 power, I know that's the same as 3 to the negative 1, because 3 to the negative 1, if I wrote it as a fraction, would be 1 over 3 to the first. So I have to make the connection, because I need to get the bases to be the same. This has a base of a prime number. I could see that 3 there, so there's a way to make both bases 3 by rewriting the fraction with a negative exponent. Normally we go from negative exponents to fractions. Like on my calculator, if I asked it to do 3 to the negative 1 power, it would tell me that that's 1/3. Well, I can go backwards from 1/3 to 3 to the negative 1 power. Now I have to pull out something else I remember from chapter 4. If I have one base with 2 exponents, I multiply the exponents. So this is going to be 3 to the negative 1 times x equals 3 cubed. And now I have the bases the same, and when you get the bases the same, you can set the bases, drop the bases, and set the exponents equal to each other. And this will take me to my answer. By dividing by negative 1 on the left side, you get x. On the right side, 3 divided by negative 1 is negative 3. In general, I wouldn't expect any intermediate algebra student to attack this problem using the same base approach, because if you look at the logarithmic approach, one line essentially, the same base approach, kind of 10 lines. So this approach I would only use if it's painfully easy, if it basically takes about the same amount of work. So, and on the test, you'll have complete freedom to solve using either method. If there's an x and an exponent, the logarithmic approach will always work. This make the bases the same approach will work for some of the problems, but you'll be able to tell if you use this approach and you get a nasty decimal answer, then this approach is not even possible. 8's not so hard using both approaches, so I'll do them with both. So logarithm method. And then the same bases. So the logarithm is constant. It doesn't vary from problem to problem. The same basis varies depending on the trick that you need to pull out to make the bases the same. So for the logarithmic approach, I'm going to write the left side with a log. The 3 is the base. It's staying the base. I'm going to switch the 243 and the 5 minus x. And I want to solve for x before I use my calculator. And I like my x being positive. And I'm going to start off by adding x to both sides. It's not like a deal breaker if you don't do this, but doing this is going to give me the positive x that I really want to have. And now I'm going to minus the logarithm from both sides. And you could definitely get the right answer solving this problem a little bit differently than me. So if you're working ahead of me, you can definitely do something a little bit different. This is just what I chose to do to get the x solved for, because I want the x to be solved for before I pull out my calculator. I'm going to do this on my calculator. Could do it in my head, but I'm going to pull out my calculator because it's quicker and more accurate. So 5 minus the log base 3 of 243. So it's 0. It doesn't mean no solution. 0 can be an answer, so let me go ahead and check. The original problem is 3 to the 5 minus x equals 243. For my answer to be correct, it should be 3 to the 5 minus 0 equals 243. So 3 exponent 5 minus 0. And I get a true statement, so I know I haven't made a mistake. The same base approach is fortunately not that hard for this, because 243 I can turn into a 3 really quickly. I'm not going to work on the left side because the 3 is prime, but on the right side, 243 equals shift prime factor, I get 3 to the 5th. So I can rewrite this as 3 to the 5 minus x equals 3 to the 5th. I was able to write both sides with the same base, so I'm going to drop the bases and set the exponents equal to each other. And I don't like that negative x. If you live with the negative x, it's okay, but you're going to have to divide by a negative 1. If you subtracted 5 from both sides and got negative x equal to 0, I want to know not what negative x is, but what positive x is. And negative x really means negative 1 times x. And to make that negative 1 into a positive 1, I divide both sides by a negative 1. On the left side, the two negatives cancel to be positive. I'm left with a positive x. On the right side, any fraction with 0 in the numerator is equal to 0. So again, both methods give me exactly the same solution, so they don't conflict. It's just that one method might be easier than another, and it's good to be able to do both strategies and pull out the one that's quicker when it's appropriate. 10 and 12 are both problems that have exponent tricks that make them hard to do without logarithms. But with logs, they're easy. For 10, I'm going to write the word log if I'm solving it with logs. The 27 is going to be the base because it's the base of the exponent. I'm going to switch the 3 and the x. I'm going to figure out what this equals to. So logarithm base 27 of 3. So this says 1/3 equals to x. That should be my answer. I'm going to go ahead and check. So for the checking, I should go to the original problem, 27 to the x equal to 3, and change the x to 1/3. So 27 up arrow fraction 1/3. And I get 3 equal to 3. So I've checked, I know my answer is right. The same base approach, this same base approach starts to get hard. So in order to handle this, the 3 is a prime number. If I want to, I could give it an exponent of 1. And I can definitely, on the left side, write 27 as a power of 3, because I know that 27, its prime factoring, is 3 cubed. So I can rewrite the left side with a base of 3. In order to do this, I have to think of the left side like that. And then when I write 27 as 3 cubed, because the prime factoring for 27 is 3 cubed, I'll have two exponents that apply to the 3. I'll multiply those exponents to drop the parentheses that I temporarily inserted. So with a few steps, I can write both sides with the same base. And if I can get each side written with the same base, then I can drop the bases and set the exponents equal to each other. And then it's just one step. I just divide by 3, and I'll get the same answer. So the methods, if you can do them both, lead to the same answer. And anytime the logarithmic approach gives me a positive or negative integer or a fraction, it's possible to use the same base approach, but it may not be desirable. 12 has exactly the same trick as 10 by hand. So again, I'll do them both ways. So the logarithmic approach, I write the word log, the 49 becomes the base, and I switch the 7 and the x. I'm done. I just need to figure out what that equals to. So the log base 49 of 7, I get 1/2 equals to x. That should be my answer, and I'm definitely going to check that. Anytime I have a problem with an equal sign, I should check. 1/2 power is the same as square root. So when I put 49 to the 1/2 equals to 7, I know that that checks already because 1/2 power is square root of 49 is 7. But I'll check it on my calculator because it's the way to go. So left side is 49 to the 1/2. When I simplify it, it comes out to be 7. I'm going to use the same trick as problem 10 to do this by hand. So 49 to the x equals 7. I'm going to emphasize that 7 is 7 to the first. I'm going to separate the 49 from the x a little bit to help me with my prime factoring and simplifying. 49, its prime factoring is 7 to the second power. So I can write the left side as 7 to the second power to the x equals 7 to the first. Multiply those exponents, I get 7 to the 2x equals 7 to the first. I have the bases the same, so now I drop the bases and equate the exponents. I finish off by dividing by 2. So the same base approach is something you're not responsible for in terms of the test, because the logarithmic approach, anytime a problem has an x and an equal sign, the logarithmic approach will take you to the answer, and it's probably more efficient than the same base approach for most problems. After we get through problem 12, I give you problems that look the same, but my instructions say use logarithms to solve, because the answers will have nasty decimals and they can't be solved without logarithms. So I probably should say round to something. Let me round to 3 decimals. The more when you have a rounded answer, the checking doesn't work perfectly, and the more decimals you include, the better the checking works. So logarithmic approach, because there's an x and an exponent, I'm going to write the word log. The 2 is going to be the low part. I'm going to switch the 10 and the x. In my calculator, I don't know if it's going to give me a decimal for this or not. So logarithm, I think it will. Logarithm base 2 of 10. Yeah. So I'm going to write for my answer the decimal in the third position is a 1. It's either going to stay a 1 or round up to a 2. Because the 9 after there, I'm going to write 3.322. And I'm going to put a squiggly because it's a rounded answer. So 3.32. And instead of writing the 1, I'm going to round the 1 up to a 2. And I'm going to say that's approximately x. So that's my rounded answer. And now I'm going to check. So the original problem says 2 to the x equals to 10. I want 2 to the 3.322 3 to the 3.322 to be approximately 10. It's a rounded answer. I don't expect it to be exactly 10, but it should be close. So let me do this. 3 to the 3.322, and I get, really, oh, it's 2, duh. Should be 2 to the 3.322. I don't know why I changed out of the 2. So 2 to the 3.322. And I get 10.00049. And that's pretty darn close to 10. I'd never expect a rounded answer to check exactly, and it's pretty darn close. That's, within 3 decimals worth of accuracy, and that's all I can expect. 16, if I'm clever, I'll solve the problem on my calculator cleverly. But 16 I can do exactly the same way. I'm going to write the word log. The e is going to be the base. I'm going to switch the 1.15 and the x. And now I'm going to pull out my calculator. two ways to do this on my calculator, the non-clever way and the clever way. The non-clever way is just to enter this. I type the log button. I notice that the e's on the x times 10 to the x key in red, so I hit alpha, the x 10 to the x key, and then type in 1.15, and I get 0.1397. This 7 tells me to round that 9 up to a 10, and then I need to round the 3 up to a 4. So I'm going to write 0.14 for my correct answer. What you should know is that log base e is shorthand for ln, and it'd be more efficient on my calculator to use the ln button. If I would have typed ln of 1.15, I would have gotten exactly the same decimal, because ln and log base e have the same meaning. Doesn't matter which you did. A lot of calculators don't have just a special e button like this without the exponent, so on a lot of calculators the ln method was kind of the only method. Regardless, I'm going to write 0.14. I don't need to write the 0 after the 4, and I'm writing squiggly lines because it's an approximate answer, not an exact answer. Now I'm going to check, because anytime I solve a problem with an equal sign, I should be able to check. So it should be the case that e to the 0.14 power is close to 1.15. Again, I don't expect it to be exactly 1.15. So shift ln 0.14 power, and I get 1.15027, and that's close enough to 1.15 for me to believe that my answer is correct. The next three problems, or maybe even four, 18, 20, 22, and 24 are here for a purpose. The purpose is they're preparing us for the word problems that we're going to need this skill. So the difference between the next few problems is that there's a number on the side that has the exponent that doesn't apply to the exponent, and I need to divide it away first before I put it in logarithm form. So I'm still going to use logarithms to solve, but the logarithm strategy needs the side that has the x in the exponent to not have something that the exponent doesn't apply to. And the exponent here only applied to the 3, it didn't apply to the 4. I needed to get it to the other side. Now I'm going to break out my logarithms. The 3's the base, it's going to stay the base, and I'm going to switch the 6 and the x. And then let me pull out my calculator to do log base 3 of 6. And I get 1.63. That 9 is going to round the 0 to a 1. So I'm going to write 1.631 is approximately x. And then I'm going to attempt to check. The original problem is 4 times 3 to the x equals to 24. So I'm going to see if 4 times 3 to the 1.631 power is about 24. So 4 parentheses 3 exponent 1.631. Close out my parentheses, and I get 24.001, 24.00185. And again, that's approximately 24. That, again, I don't expect an exact checking because it's a rounded answer, but it's good enough. 24.001. If I round it to the nearest integer, it rounds to 24. On 20, it may look like the 3x applies to both the e and the 14, but it doesn't apply to the 14. It only applies to the 3x. So just like the last problem, I'm going to divide to isolate the piece with the exponent. And when you get into your checking, you'd find out if you skip this step that it was wrong. So on the right side, I need to do 42 over 14. Turns out to be 3. So dividing both sides by 14, I get e to the 3x equals 3. Now it's ready for a logarithm. So I'm going to write the logarithm. The e is low, I'm going to switch the 3 and the 3x. And again, before I use my calculator, I like to solve for the x. So I'm going to solve for the x before I pull out my calculator by dividing by 3. I have some flexibility on the left side. I could enter this on my calculator, or I could enter this on my calculator. They're both going to be okay. I'll show you they both give the same answer. This top one, if I went fraction log base alpha e of 3 over 3, I get 0.366. After the 6 is a 2, so I wouldn't round this 6 up, and I'd leave that for an answer. If I did the bottom version, fraction ln of 3 divided by 3, I get the same 0.366 because log base e and ln mean the same. Ln is shorthand for log base e. And generally, when I'm using my calculator, I don't take the time to write log base e of 3 because that requires me to use the alpha button, type the e. I generally use ln because they give the same thing, and ln is shorthand. It's preferred in some sense. Now I'm going to check. So for checking, the original problem was 14 times e to the 3x equals to 42. I'm going to see if 14 times e to the 3 times 0.366 is about 42. So 14, shift in ln for the e with the exponent, and then 3 times 0.366. And I get 41.974 is about 42. My 41.97 at least rounds to 42. You're not gonna get a wrong answer that checks that closely unless you're just really unfortunate. So I think that's close enough. 41.97 certainly isn't 42, but it's close to 42. If I would have carried more decimals, I'll show you. If I would have carried like ln of 3 over 3, if I would have done 0.3662 even when I checked and carried an extra decimal, if I did 14 shift ln 3 times 0.3662, if I carried 4 decimals, look how much closer it is. It's 41.999 is approximately 42. So there's a flaw to rounding in that the less decimals, the shorter you write your answer in terms of decimals, the further off your rounding is going to be. So if I would have required 4 decimals worth of rounding, then it would have been maybe more believable that the answer checks. But it does check. 22 and 24 are repeats of this problem. I want to get real good at doing this because the word problems that we need to solve in this section have this solving strategy. So the 0.04x doesn't apply to the 3. I'm going to divide both sides by 3. On the left side, the 3's are going to cancel. I'm going to be left with e to the 0.04x. On the right side, 12 divided by 3 is 4. Now I'm going to put it in logarithm form. The e is going to be low. I'm going to switch the 4 in the 0.04x. So I get the log base e of 4 equals 0.04x. I'm going to divide both sides by 0.04 to get the x solved for before I use my calculator. On the right side, the 0.04's are going to cancel. I'll be left with the x. On the right side, I have something that's ready for my calculator. And on my calculator, I'm going to enter it with the ln as opposed to the log base e. So I'm going to go fraction ln of 4 divided by 0.04, and I get 34.657 is approximately x. And then I'm going to check again, because anytime I have a problem that has an equal sign, is just that not that hard to check, and I should check. So it should be the case that 3 times e to the 0.04 times 34.657 is about 12. I'll just remind myself that this answer really is 34.6 0.573559. I might check that as well. So let me check. 3 shift ln for an e with an exponent, 0.04 times 34.657. It gives me that's close enough. That gives me 11.9998 is approximately 12, and I feel good enough about that that I'm not even going to check the longer decimal answer. So this is what I'd write for my answer to problem 22. Move on to 24. Same style of problem. I wanted to hammer these down a little bit because the only word problems that we do in this section require this strategy. So divide by 3, divide by 3. I get e to the 0.05x equals 7. Write it in its logarithmic form. All the problems between 1 and 24 can be solved by writing them in logarithmic form. So this gives me the log base e of 7 equals 0.05x. I divide both sides by 0.05 and not the x. On the right side, I get the x. On the left side, I get something I need to use my calculator. I like doing the ln as opposed to log base e, but both will work. If I decided I wanted to do log base e, I'd go fraction, log, alpha, e, log base e of 7 over 0.05. You don't need to use the ln. Still that gives me 38.918 is approximately x. And had I done fraction ln of 7 over 0.05, I'd still get 38.918 is approximately x. So it's just easier. And now I'm going to check. The original problem was 3 times e to the 0.05x equals 21. I'm going to see if 3 times e to the 0.05 times 38.918 is close to 21. So 3 shift ln 0.05 times 38.918, and I get 20.999786. That's definitely good enough for me. That's definitely close enough to 21 that I believe myself. So there's only one bank of word problems I'm going to do in this section, and decided I was going to do those next. I thought I put them right in place to do. Where are those word problems? Ha, here they are. I want to do these out of order because they fit so perfectly right now. So the only word problems in the section we're going to do are the word problems from 60 to 63. And the other group of word problems we're going to skip. So these will be the last word problems for the semester that we need to do. They're money word problems, and somewheres in the money word problem I see the word compounded continuously. We have two money formulas. The one formula that we learned first was A equals P times 1 plus R over N to the NT power. That we use if the word after compounding was like monthly, quarterly, yearly, daily. And then we had the formula A equals P e to the RT. And that is the formula we use when the word after compounded is continuously. So when you're given a money word problem, which are the only kind of word problems that are going to make it on the test, you have to decide which formula you're going to use. If you glance at the problem, you look at the word compounded. If after compounded you see quarterly, monthly, daily, yearly, use the formula with the N. If you see the word continuously, you use the A equal PE to the RT formula. And again, the A is the amount of money in the future. The P is the starting amount. The R is the interest rate, but as a decimal. And the T is the number of years. So in order to solve a money word problem using the A equal P e to the RT formula, the E is 2.718. I don't need to put it in here as an unknown. I know what it equals to. But in order to solve a money word problem, you have to have numbers for 3 of the 4 letters so you can solve for the missing letter. So as I read through the problem, the first number I see is 1,000, and before the word 1,000 it says it's the initial investment, so that's going to be the P. So in this problem, the P is going to be $1,000. The next number I see is 6% interest. That seems like an interest rate, and as a decimal, I'm going to write 0.06 for the interest rate, and I'm out of numbers, which really makes that kind of not pleasant. So either I need to, with my reading ability, figure out a number to put in for the number of years, or I need to figure out a dollar amount for the money in the future. So as I read through the problem, there's a word that's supposed to help me decide on a value for one of these two, and it's the word triple. And how long will it take $1,000 to triple? So what the question is, how long? I'm actually solving for T because I want to know how many years it takes for this to happen. And the number that wasn't given but hidden is the future amount of money, because tripling 1,000 takes 1,000 and grows it to $3,000. So this was the hidden dollar amount. Now that I have 3 of the 4 amounts, I can solve this by plugging the numbers into the formula. So A is going to be 3,000. P is going to be 1,000. E is going to stay E, and then I'm going to get 0.06 times T. This is supposed to be just like the problems that we've done, but it's backwards because the exponent's on the right-hand side. I'm going to solve it exactly the same way. It might feel backwards. If it feels backwards to you, you can rewrite the problem like this. Equality is commutative, so you can flip the equation around backwards, and it still has the same meaning. Now this looks just like the problems that we solved, more or less. So I'm going to divide by 1,000 to free up the E, and this gives me E to the 0.06 T equals to 3. Then I'm going to write it in its log form. The log base E of 3 equals 0.06 T. I divide both sides by 0.06. And I'm going to pull out my calculator. I'm going to go the ln of 3 over 0.06 equals to T, but you can do the log base E if you like that better. So fraction ln of 3 divided by 0.06. I get 18.31. It says round to 1 decimal place, so I'm going to say 18.3 is approximately T. And I'm going to check into this version right here. I'm going to go, or that version right there, let me just check it right in line. I'm going to go, is 1,000 times E to the 0.06 times my answer 18.3. Is that about 3,000? It's 2,998. That's close enough to 3,000 for me. If I didn't think it was close enough, I can go back to my answer and maybe take a 2 decimal rounding or a 3 decimal rounding, and it'll check better. But I think it's only $2 off. I feel good enough about that. So I'm ready to write my answer, and I'm going to write the word years. So it's going to take about 18.3 years for my $1,000 to triple and grow to $3,000. All right, 62, another money word problem. It's a little bit easier, I think. You might not feel the same. So in money word problems, I look for the word after continuously. Because the word after continuously is after the word compounded, should I say. After the word compounded, if you see continuously, you use the money formula with the E. So I'm going to use the A equals P, E to the RT formula. I need to get 3 of the $4 amounts. The first 3 of the 4 amounts. The first amount I see is $100,000. That's the initial investment. That's going to stand for P. The next number I see is $1 million. That's the amount of money that I'm going to have in the future. So that's going to be the A. And the other number I see in the problem is 4%. That's the interest rate. I'm going to make it as a decimal. I'm going to find out how long it's going to take my $100,000 to grow to $1 million by putting the numbers into the formula. So I'm going to go $1 million for A equals 100,000 for P times E to the R, which is 0.04, times T, which is unknown. If this feels backwards to you, you can flip it around and say 100,000 times E to the 0.04 T equals $1 million. And then this is like the last 4 or 5 problems that we've solved by hand. So divide both sides by 100,000 to free up the E. I could do that division in my head, or I can use my calculator. 1 million divided by 100,000. It's not that hard to do. You just lump enough zeros. So 1, 1, 2, 3, 4, 5, 6. That's 1 million over 1, 1, 2, 3, 4, 5. That's 100,000. I get 10. I could have just canceled out a bunch of zeros. I could have just done cancel, 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 and been left with a 10. So I get E to the 0.04 T equals to 10. Write it in its log form. The log base E of 10 equals 0.04 T. Divide both sides by 0.04. And the right side gives me T. The left side I can use my calculator. I could enter that. Or, because it's easier to enter the ln of 10, I could do that. Both would give me exactly the same. So if I wanted to, I could go fraction log base E of 10 over 0.04. Again, it says round to 1 decimal, which makes my checking not so good. So I get 57.6 is T. And again, if I just did fraction ln of 10 over 0.04, still get the same 57.6 rounding to 1 decimal. And it's easier. I'm going to check up here, and I'm not even going to write my checking. And I'm going to check 57.5646. So when I check, I'm going to do this. I'm going to say, does 1 million equal to 100,000 E to the 0.04 times that? And I'm going to use all those decimals in my checking because because the more decimals you carry, the more accurate your answer. Even though I'm asked to round to 1 decimal, I'm going to check this 4 decimal. So I'm going to go 100,000, 5 zeros, and then shift ln, and then 0.04 times 57.5646, because I needed to go 0.04 times t, and I just didn't feel like writing it there because I didn't have room. When I hit equals, I get $999,998.90, and that's close enough to $1 million for me that I think my checking is okay. It's only off by $1.10. If I would have carried more decimal, it would have even been more accurate. So my answer is about 57.6 years for my $100,000 to grow into $1 million. So if you're feeling, like you need a break right now, this is the perfect time to take a break, because this is going to segment the section. So the first 24 problems They all had x's in an exponent. They could be solved with logarithms. The only word problems that we're responsible for in this section, they have t's in the exponent, which is the same as having x's in the exponent. It's just a different letter. So they're all that style of problem. The next group of problems, they all start with logarithms, and they're a new style of problem. And when you have a problem that has logarithms and an equal sign, you like to get rid of the logarithms. So if you need a break right now, there's still another 25, that's about 13 more problems or so that I have to do. And they're a different strategy. So if you're not ready for a half hour of a different style of problem, take a break, come back, and watch it later. If you're ready, I'll just do these now. So for each of these problems, I want to get rid of the logarithms, and it kind of depends how the problem is set up, how I'm going to get rid of the logarithms. 26, 28, 30, 32, 34, 36, 38. Up until 38, I only see one logarithm. And when I only have one logarithm and an equal sign, I'm going to do exactly the same thing. I'm going to scratch out the logarithm and switch, kind of. So up through 38. So from 25 through 38, I'm going to do these all the same. So I'm going to scratch out the log to get rid of the logarithm. In this problem, I'm going to leave the 2 low, and I'm going to switch the x and the 3. So the original problem is the log base 2 of x equal to 3. I'm going to scratch out the log. I'm going to switch the 3 and the x, and I get 2 to the 3rd power equals the x. I don't need my calculator for 2 to the 3rd power. I know that in my head. I claim that this is the answer, but I should definitely check. So the original problem is the log base 2 of x equal to 3. I want to make sure that the log base 2 of 8 equals to 3. So again, I'll rely on my calculator, even though I probably really don't need to. Log base 2 of 8. I get 3 equal to 3, so I've checked. So for every problem between 25 and 38, my very first step is going to scratch out the log and switch. Once I get past 38, I'll do something different. Well, I spoke too soon. If I scratched out the log now, I'd look at, and it would say x equal to 0. That's not good. For the scratching out to log and switching strategy, you have to see the base. So if a logarithm's written in shorthand notation, you need to get rid of that shorthand notation. So ln and log base e are the same. Now I'm ready to scratch out the log and switch. So scratch out the log, switch the x and the 0. I'm going to write e to the 0 equals x. I don't need my calculator for that, but if I pulled out my calculator, it was not going to let me down. So I'm going to go shift ln e to the 0. Calculator tells me e to the 0 is 1 because anything to the 0 power is 1. That should be my answer. I should be able to check. The original problem is the ln of x equal to 0. I'm going to make sure that the ln of 1 equal to 0. My calculator likes the parentheses, and it's kind of nice to see them anyways. So ln of 1. When I do that, I get 0 equal to 0, so I know my answer is correct, and I've done that properly. Ooh, 30's going to be ugly, but I can deal with it. So 30, scratch out the log and switch. I get 4 to the negative 2 power equals 5x minus 6. I know that 4 to the negative 2 power, what it equals to, but if you don't, 4 to the negative 2 power is 1/16. So this gives me 1/16 equals 5x minus 6. I'm going to add 6 to both sides. 1/16 plus 6, I don't feel like doing that right now. That's 6 and 1/16. So let me try that. 1/16 plus 6. No. Messed up on that. Plus 6. I get 97 over 16 equals to 5. I think I had problems entering something like 5x it equals to. I divide both sides by 5. And I'm going to get x equals to, I should probably do this by hand, but so fraction in the numerator of 97 over 16 divided by 5, and I get 97 over 80. Let me solve this by hand and show you how I would solve it by hand real quickly. From this point right here, if I was working by hand and I had 1/16 equals to 5x minus 6, that fraction's going to mess me up like crazy, so I'm going to multiply everything by 16 to clear the fractions. So again, my answer 97 over 80, I just did, nice calculator work, but by hand I could still get there. Multiply by 16 to clear the fraction. 5 times 16 is 80. That would give me an 80x. 6 times 16 is 96. So I can get 1 equals 80x minus 96. Add 96 to both sides. Gives me 97 equals to 80x, and then divide by 80. Still get 97 over 80 equal to x. Didn't have to rely on my calculator. Didn't look so impressive. Before I commit to say that this is my answer, I'm going to check, and I'll just check up top here. So I need to make sure that the log base 4 of 5 times 97 over 80 minus 6, make sure that equals -2, and I'll probably use a parentheses on my calculator for that. So log base 4 of 5 parentheses fraction 97 over 80 minus 6, close out my parentheses, so that looks a lot like what I wanted to enter. If it says -2, I feel good. It says I made a mistake enter. And it must need a time sign there then? Really? I might put a time sign in. I don't know what I did wrong. I'm starting over. Log base 4 of 5 parentheses fraction 97 over 80 minus 6, close my parentheses. Really? I don't like this. What's going on here? 5 parentheses 97 over John. 5 parentheses fraction 97 over 80. 97 over 16 minus 6 equals 116. I'm going to try one more time. I really don't know what I'm doing wrong. Log base 4 of 5. I'll do a times sign. Times fraction 97 over 80 minus 6. Now it gives me the -2. For some reason, it just wasn't liking the parentheses inside the parentheses. I have no idea. It should work. Log base 4 of 5 parentheses fraction 97 over 80 minus 6, close my parentheses, and it just doesn't like that. So for whatever reason, it just didn't like these parentheses, and I had to use a time sign for the times for that fraction for my checking. I'm not sure why. I don't remember running into that earlier this semester. So if I was checking by hand, I might use that parentheses, but I need a times there. Now you get -2 equal to -2, so it works perfectly. Another horrible fraction problem, but I can deal with it. It's not as horrible. Scratch out the logarithm. Switch the -4 with the x minus 3. The x minus 3 doesn't need to be in a parentheses anymore. 2 to the -1 power, 2 to the -4 power is 1 over 2 to the 4th, which is 1/16. So this gives me 1/16 equals x minus 3, and then plus 3 plus 3. And let me do that. 1 over 16 plus 3 is 49 over 16. So I get 49 over 16 equals to x. If I wanted to do by hand, 1 over 16 plus 3, I'd write the 3 as a fraction, and then I'd multiply it by 16 over 16, and I'd go 1 over 16 plus 48 over 16 to give me that 49 over 16. I'm going to try to check. I'm going to see if the log base 2 of 49 over 16 minus 3 equals negative 4. No reason to think it doesn't, but I can't do that in my head by any chance. So the log base 2 of fraction 49 over 16 minus 3, and I get negative 4 equals negative 4. So I've done well there. Should say answer. Still in the problems that are kind, and these are actually a little bit easier. Crossing out the log, leave the 2 low, switch the 5 and the x minus 1. I don't need the parentheses anymore. 2 to the 5th power is 32, so this gives me 32 equals x minus 1. Add 1 to both sides. 33 equal to x should be my answer. So I'm going to check to see if the log base 2 of 33 minus 1 equals to 5. So let me do that checking. The log base 2 of 33 minus 1. And I get 5 equal to 5. So I've checked properly. 2 more problems, or maybe 1 more problem. 2 more problems before we get to a different style. It's not any harder, it's just different. You have to be able to look at the problem, recognize that it's a different style, and know what strategy to use. So 36, cross out the logarithm, switch the 2 and the x minus 5. I don't need the parentheses anymore around the x minus 5. 3 squared is 9, so I get 9 equal to x minus 5. Add 5 to both sides. I get 14 equal to x for what I think my answer is. I'm going to check to see if the log base 3 of 14 minus 5 equals to 2. Quick check. Log base 3 of 14 minus 5, and I get 2 equal to 2. So I was trying to be consistent the whole semester. If a problem had an equal sign, it can be checked, and I do check it because there's never a reason to write down a wrong answer to a problem that has an equal sign that isn't that hard to check. And it's just pressing buttons, and I don't mind doing that. 1 more problem of the same style. 1 logarithm that I can cross out the logarithm, switch the 0 and the 3x. Fraction answer this time because 3 to the 0 power is 1. So this gives me 1 equals to 3x. I divide both sides by 3, and I get 1/3 equal to x, I believe, for my answer. For my checking, I'll see if the log base 3 of 3, and I'm going to put a times sign as opposed to a parentheses. So I'm going to check that. So log base 3 of 3 times fraction 1/3. I was afraid to use the parentheses after my last checking disaster. And this gives me 0 equal to 0, so I'm fine. So up through 38, starting at, I think, what was the problem? Starting at 25, going through 38, what each of those problems have is on the left side they have a logarithm, on the right side they have a number. They're very kind problems, kind of just a few steps to get to the answer. The next few problems, what they have in common, 40 and 42, what they have in common is there's just 1 logarithm equal to another logarithm. And for these problems, you can just drop the logs and equate the argument. So for 40 and 42, what they have in common is they look very different than the other problem. They have 1 logarithm, same base, equal to another logarithm, same base. For those problems, they're easy. You just drop the logs and equate the arguments and solve for x. I'm going to minus x and solve and add 10 to get to my answer. Even though my x is going to be on the right side, I like this better than minusing 2x and adding 4. On the left side, the x's cancel. On the right side, minus 4 plus 10 is positive 6. Or on the left side. Here, 2x minus x is 2x minus 1x, which is x, and the 10's cancel. I claim that this is the answer. Because there's an x on each side, I need to check each side. So the original problem was the ln of x minus 4 equals the ln of 2x minus 10. I'm going to see if the ln of 6 minus 4 equals the ln of 2 times 6 minus 10. So ln of 6 minus 4 is 0.693. I'll do the other side. The ln of 2 times 6 minus 10 is also 0.693. So even though they don't each reduce to nice integers, they reduce to the same horrible decimal, so I know my answer is correct. For that matter, this simplifies to the natural log of 2, and this is 12 minus 10, which is 2. They both simplify to the natural log of 2, and so they're both equal. So when you have one logarithm equal to each other, same base, they have to be the same base, you can just drop the bases and equate the exponents, or equate the arguments. So for 42, it's just like 40. I set 3x plus 6 equal to 4x. Solve for x by minusing 3x from both sides. I get 6 equal to x for my answer. Again, I should check. I go to the original left side. I'd go the log base 4 of 3 times 6 plus 6 and see if that equals the log base 4 of 4 times 6. Without my calculator, this comes out to be 18 plus 6, which is the log base 4 of 24. And on the right side, I have 4 times 6, which is a log base 4 of 24. That's actually enough for checking. I don't have to get the ugly decimals if I don't want to. But if I pulled out the ugly decimals and did the log base 4 of 3 times 6 plus 6, this left side comes out to 2.29248. And the right side, if I did the log base 4 of 4 times 6, I get 2.29248. So they come out to the same ugly decimal if I want to make them into decimals. So I didn't do many of those style of problems because they're just one step. You drop the logarithms, you set the arguments equal to each other, and you solve for x. The next group of problems, 44 and 46, what they have in common is they have two logarithms, but they're on the same side of the equation, and they have a minus sign. 44 and 46 I'm going to solve the same way. Step 1, I'm going to use the minus to divide rule. How do I use the minus to divide rule? The minus to divide rule says if I have two logarithms, same base, separated by a minus sign, I can make those two logarithms into one logarithm if I divide their arguments. We did that in section 6.6, I think, last section. Now this is just like the beginning problems. I'm going to cross out the log and switch. The only hard thing is the solving. These are a little bit different to solve, but other than that I need to cross multiply, they're not that hard. So these didn't go in the first group of logarithm problems because they had two logarithms. They didn't go in the second group of logarithm problems because there was a minus between the logarithms. So I pulled out a rule that we just learned. Now I'm going to cross out the log, switch the -1 in the fraction. Like to solve by cross multiplying. Let me get rid of that 3 to the -1. 3 to the -1 power, really? 3 to the -1 power is equal to 1 over 3 to the first, which is 1/3. So I can say this is 1 over 3 to the first, or 1/3 equals x over x plus 6. And I'm going to solve by cross multiplying. So I'm going to go this way, that way. I get 3 times x equals 1 times x plus 6. That's going to give me 3x equals x plus 6, because 1 times anything is itself. I'm going to minus x and get 2x equal to 6, and then divide by 2, and get x equal to 3. This should be the answer, but I'm going to check. So answer. I'm going to come up here and check to see if the log base 3 of 3 minus the log base 3 of 3 plus 6 equals -1. My calculator makes me put those parentheses in. So this is checking, which I do for any problem that has an equal sign. So log base 3 of 3 minus the log base 3 of 3 plus 6. So there's the original problem. And I get -1 equal to -1. So I've checked perfectly. I'm going to do 46 exactly the same way. What 46 has in common with 44, two logarithms separated by a minus. I'm going to use the minus to divide rule and then use the same strategy of crossing out the log and switching, but I'll need cross multiplying to solve. So 46, two logarithms separated by a minus. Step 1, minus to divide rule. I get the log base 3 of x minus 5 over x plus 3 equal -2. That's step 1, using the minus to divide rule. Step 2, cross out the log and switch. I get 3 to the -2 power equals x minus 5 over x plus 3. Step 3, solve by cross multiplying. Let me clean up that 3 to the -2 power. 3 to the -2 power is 1 over 3 squared, which comes out to be 1/9. So I get 1/9 equals x minus 5 over x plus 3. Solve by cross multiplying. Gives me 9 times x minus 5 equals 1 times x plus 3. 9 times x minus 5, I multiply the 9 times x and the 9 times minus 5 and get 9x minus 45. And on the other side, 1 times anything is itself. So now I'm going to minus x and add 45, minus x and add 45. On the left side, 9x minus x is the same as 9x minus 1x, which is 8x. 45's cancel. X's cancel. 3 plus 45 is 48. I'm going to divide by 8, and get an answer that I need to check of x equal to 6. I'm going to check it up here. So I'm going to see if the log base 3 of 6 minus 5 minus the log base 3 of 6 plus 3, see if that equals to -2. So checking is super important on these. So log base 3 of 6 minus 5 minus the log base 3 of 6 plus 3, and I get -2, which still does equal -2. So I've checked, I'm done. I'm gonna make up another one of these because I know I put one of these on the test. I don't know if 2's enough. So let me try to just make up one easy one. The log base 2 of x plus 2 minus the log base 2 of, I'm going to do this in my head right here. So this is going to be 3. X is 6. Of 8 minus x equals 2. Plus 6 and boom, that's 3. That's equals to 2. Lots of 2's going on here, but when I try to make up a problem, it's kind of hard for me to make up a problem this complex on the run. So just like the last two problems, two logarithms separated by a minus, I'm going to first step use the minus to divide rule and go to log base 2 of x plus 2 over 8 minus x equals to 2. Cross out the log, switch, I get 2 to the second power equals x plus 2 over 8 minus x. I want to solve by cross multiplying. I'm going to write 4 equals x plus 2 over 8 minus x. This one doesn't have a fraction that just turns, the left side doesn't turn into a fraction because it doesn't have a negative exponent. So it can make it a fraction by writing it over 1. Now I'm ready to cross multiply. I'm going to go 4 times 8 minus x equals 1 times x plus 2. Left side, I go 4 times 8 and get 32. 4 times minus x is minus 4x. Right side's just going to be x plus 2. I like my x's to be positive. I'm going to minus 2 and add 4x to both sides. On the left side, if I minus 2, 32 minus 2 is 30. The 4x's cancel. On the right side, x is 1x plus 4x is 5x, and the 2's cancel. Divide by 5, divide by 5, and 30 divided by 5 is 6. I think the answer is 6. I'm going to try to check it. I have a lot of room to check this, so I'm going to try to check it right here. So for my checking, I'm going to go to the original problem and see if the log base 2 of 6 plus 2 minus the log base 2 of 8 minus 6, and see if that equals to positive 2. So quick check. Log base 2 of 6 plus 2 minus the log base 2 of 8 minus 6, and that equals to 2. So I've checked. I want to do even one more of these because the last style of problem I know I don't usually put on the test, but this I do put on the test. So let me real quickly think of one. Good enough. How about we try this one? So again, not on the handout, but I don't know if there was enough of these problems to do, so I wanted to give you more. So log base 4 of x plus 12 minus log base 4 of x equals to 2. Structurally the same as the last 3 problems that I did. Two logarithms, same base, separated by a minus. First thing I do is use the minus to divide rule. And when I use the minus to divide rule, that takes the two fractions and makes them into 1. Now it solves like a regular logarithm problem. I cross out the log and I switch. I'm going to get 4 to the second power equals x plus 12 over x. I like to solve these fraction problems by cross multiplying. 4 squared is 16. Doesn't naturally give me a fraction, so I need to force a fraction by putting it over 1. So I'm going to go 16 over 1 equals x plus 12 over x and cross multiply. Doesn't matter which way I cross multiply. one way I'm going to do is 16 times x. The other is 1 times x plus 12. So this is going to give me, really, square, boom, chicka boom. Oh. I feel like I'm making a mistake, so let me, before I get too far into this, first of all, make sure the answer that I think checks. Sorry. There's a danger of making a problem on the fly, and I don't know either. Should I change the problem or live with the nasty answer? I'm going to live with the nasty answer. On the test, you will not get answers that are so nasty, but I'm going to have to live with a horrible decimal fraction answer, but it's not that hard to check. So I didn't want the answer to come out to be a fraction because they won't on the test, but this one's going to come out to be a fraction. It's okay though. Two fractions separated by a minus, use the minus to divide rule to make one logarithm. Scratch out the logarithm, switch, set it up to solve by cross multiplying to solve. I'm going to minus x and minus x. That will give me 15x equals to 12. And then divide by 15, and I get the answer of a fraction. And that's not going to happen on the test for these dividing problems. That's why I stumbled for a second. I'm like, oh, I don't want that, but I'm just going to live with it. So I'm going to try to check. Not that hard to check. So I'm going to go the log base 4 of 12 over 15 plus 12 minus the log base 4 of 12 over 15, and see if that equals to 2. If it equals to 2, I feel good. So log base 4 of fraction 12 over 15 plus 12. First one done okay, and then minus the log base 4 of fraction 12 over 15. Let's hope I see 2. And it comes out to 2, so I've checked perfectly. So guaranteed that the two problems that I just made up, as well as the problem 46 and 44, those are all structurally the same. When I look at them, two logarithms, same base, separated by a minus, all 4 times. Some of them equal to a negative number, which is actually easier because the fraction comes out kind of naturally. I don't have to force the fraction. Or equal to a positive number where I still want to solve by cross multiplying. One of these will be on the test, and it's on the review. I don't think one of these is on the test nor the review. So I'm going to do 48. I'll do them both, but 48 and 50, if you wanted to stop the video and not watch the rest, it's okay. If you're going on the Math 151, you're going to see one of these again, so in that class, so it can't hurt. For 48 and 50, I need to use the add to multiply rule to make the left side into one logarithm. So I'm going to go left side, logarithm base 2 of x plus 2 times x equals to 3. I need to do that multiplying. That multiplying has me go x times x and 2 times x. So I can rewrite the left side as a log base 2 of x squared plus 2x equal to 3. This is not radically different than what I've done for the last 4 problems, but the bad thing is there's a square I'm going to have to solve by factoring, and I'm going to get an answer that doesn't check. Usually on these problems where you used to add the multiply rule to make one logarithm out of the 2, you generate answers that don't check. So step 1, step 2, cross out the log and switch. So cross out the log. I'm going to leave the 2 low. I'm going to switch the 3 and the x squared plus 2x. This gives me 8 equals x squared plus 2x. My writing is really deteriorating. Solve by factoring. So to solve by factoring, the problem needs to be set equal to 0. I minus 8 from both sides, and I get 0 equals x squared plus 2x minus 8. Easy factoring is factors into x plus 4 times x minus 2. So I go x plus 4 equal to 0, x minus 2 equal to 0, minus 4, I get x equal to minus 4, plus 2, I get x equal to 2. The minus 4 is not going to check. When I go to check, I'll check the 2 first. So for x equal to 2, I'll go the log base 2 of 2 plus 2 plus the log base 2 of 2, see if that equals to 3. That's the one that's going to work, and that's the only one I'm going to put in my solution. So I'm going to go to log base 2 of 2 plus 2 plus the log base 2 of 2, and I get 3 equal to 3. That one will check, but the negative 4 is going to give me an error because logarithms are only defined for numbers bigger than 0. So when I do the log base 2 of negative 4 plus 2 plus the log base 2 of negative 4, my calculator is going to give me an error message of some sort because this is asking me to take the logarithm of a negative number, and it doesn't work. So this is not going to be a solution, and the only solution is going to be the 2. So when I do log base 4 of negative 4 plus 2 plus the log base 2 of negative 4, I know it's going to give me an error message. I can't get around that error message. So the only answer to problem 48 is the positive 2. It's the only one that checks, and I shouldn't include an answer that doesn't check. So for my answer, I'm going to write x equal to 2 and be done with it. I'm going to do 50 the same way. Again, 48 and 50 that have the two logarithms separated by a plus sign that you have to use to add the multiply rule. They generally produce solutions that don't check and won't be on the test. But the ones that I did 4 of with the minus to divide rule, those will be on. So if you're watching this, this is good for you. If you're not, then you won't know this anyways. So first, using the add to multiply rule to make the two logarithms into one. Multiply x times x and get x squared, x times 12 and get 12x. Cross out the logarithm, switch. So I get 4 cubed equals x squared plus 12x. 4 cubed is 64. So it gives me 64 equals x squared plus 12x. These, because I have the square and an equal sign, I need to solve by factoring. So I minus 64 from each side, and I get 0 equals to x squared plus 12x minus 64. I can solve it by factoring, and I will, but if you couldn't factor this, you can use a quadratic formula. But I do factoring well in my head, and it's the last new problem for the semester. Pull out the quadratic formula if you can't factor this. But 16 times negative 4 is 64, 16 minus 4 is 12. That's the way it's going to factor. Quadratic formula using a equal to 1, b equal to 12, c equal to negative 64 will give you the same answers that the factoring gives you. It just takes me a little bit longer. So I get x equal to negative 16, which isn't going to check, and x equal to 4 that will check. Again, I'll sneak the checking in up here. The 4, if I check the x equal to 4, I get the log base 4 of 4 plus the log base 4 of 4 plus 12, and that is going to equal to 3. So do that one real quickly. The log base 4 of 4 plus the log base 4 of 4 plus 12. That gives me 3 equal to 3. Usually these factoring logarithms lead to solutions that don't check. When I try to check the x equal to negative 16, I'm going to get an error because logarithms are only defined for numbers bigger than 0. So immediately right there, I wouldn't even use my calculator because I know that's going to give me an error. And that tells me that that's not a solution. I won't get a true statement. If I tried to check this full out and did the log base 4 of negative 16 error plus the log base 4 of negative 16 plus 12, which is going to be another error, I get an error, and an error doesn't equal to a 3. Because an error doesn't equal to 3, negative 16 doesn't check. And for my answer, I only include solutions that check. I don't include solutions that don't check. So I'm going to write x equal to 4 and be done. Again, the last two problems in this section, 48 and 50, I won't put those on a test. You don't have to worry so much about them. But the 4 problems before with the minus between, you do have to worry about them. So that's the end of the new material for the whole semester. You should, take the time now to really get this section understood as best you can, and then get that review done. If you can do all the problems on the review, you should be completely ready for our last test and hopefully not have to take the final. If you need some help after you do the Chapter 6 test to figure out what your grade's going to be if you skip the final, come visit me and I'll help you figure that out.